It's 3 a.m., your phone is buzzing, production is down, users are complaining, and your heart is racing. But here is the question that paralyzes your team. Is this bad enough to escalate? How much downtime is acceptable? Did we break our commitment to users? Or is this within tolerance? And the next morning, after a 4-hour incident, the real conflict begins. Product says, we need to move faster, we are losing to competitors. And engineering says, we need to slow down, the system is breaking. And both are right, both are acting rationally. And without a framework to bridge this gap, your organization will tear itself apart. What's the right amount of reliability? How do you measure it? And how do you balance it with the speed of innovation? These aren't just technical questions. They're fundamental to how modern engineering organizations operate. And today, we're going to answer them using one of the most powerful frameworks in software engineering, Site Reliability Engineering's approach to SLI, SLO, and SLA. By the end of this video, you understand the theory and principles behind SRE. In part 2, we'll show you exactly how to implement this in your organization with real-world case studies. So let's dive in. And before we talk about the solution, we need to understand the problem. Let's go back to the early 2000s. In the pre-SRE era, operations teams measured reliability in a deceptively simple way, just uptime. We have 5 nines, they would proclaim, meaning 99.999% uptime, and that sounds impressive. But here is what they were actually measuring. Are the servers responding to health checks? That's it. The server could be returning errors to every user request, taking 30 seconds to load the page, or corrupting data, and the dashboard would still show green. They measured what was easy, but not what mattered. Then came the DevOps revolution. The promise was beautiful. Break down silos between development and operations. Deploy faster. Automate everything. You build it, you run it. And it worked. Sort of. Teams started shipping code multiple times per day instead of once per quarter. Cycle times collapsed. Innovation accelerated. But a new problem emerged. With velocity came instability. And when things broke, the same old question came back. Whose fault is this? Even in DevOps organizations, a fundamental tension remained. Developers were incentivized to ship feature fast. Operations teams were incentivized to keep things stable. These goals are in direct conflict. Think about this structurally. If your performance review depends on shipping features, what do? You ship as fast as possible, maybe cutting corners on testing. If your performance review depends on uptime, what do? You resist all changes, because changes break things. And both groups are behaving rationally within their incentive structure. The problem isn't the people, it's the lack of a shared framework for making trade-offs. Even teams that embrace DevOps faced another challenge. They were drowning in metrics, but starving for meaning. Your monitoring system tracks thousands of metrics: CPU utilization, memory pressure, disk I/O, network latency, database connection pulse, and every metric has an alert. Disk usage above 80%? Alert. Response time above 500 milliseconds? Alert. This is called alert fatigue, and it's a silent killer of reliability. When everything is urgent, nothing is urgent. You train your team to ignore alerts because most of them don't actually indicate user impact. And then, when a real incident happens, you miss it in the noise. And then, modern architecture made everything exponentially harder. A decade ago, you might have one monolithic application, one database, and a load balancer. Debugging was straightforward. The monolith is either up or down. Today, your simple user flow might touch 20 different microservices, 3 different databases, 2 caching layers, a message queue, and 4 external APIs. One service has a slow database query, and suddenly your entire user journey fails. How do you even define reliability in this context? Is it reliable if service A is up but service B is down? What if service A is up but responds in 5 seconds instead of 50 milliseconds? Let me make this concrete with 2 failure modes. First one is over reliability, the perfectionism tax. For example, we have team that spend 80% of their engineering time on reliability work for a system that users accessed once per week. They had 4 nines uptime for an internal analytics dashboard. The cost, they missed their market window. A competitor shipped a good enough product at lower reliability and captured the market. So, perfect reliability killed innovation. The opportunity cost of over-engineering reliability is measured in millions of dollars and lost market position. On the other side, we have under-reliability. In 2017, AWS S3 went down in US East 1 region for 4 hours, caused by human error during routine maintenance when an engineer accidentally removed more servers than intended. Thousands of businesses couldn't function. The internet broke. Another example is Knight Capital. This company lost about $440 million during the first 35 minutes of trading due to a deployment issue. The company was acquired shortly after, and they never recovered. But more common than spectacular failures is death by 1,000 cuts, incidents every few weeks, apology emails to customers, trust eroding, customers quietly moving to competitors. So, here is where we have arrived. Perfect reliability is impossible, and attempting it kills innovation. But inadequate reliability kills trust and potentially the business. So, how much reliability is enough? And how do you measure whether you are meeting that target? And when you are not meeting it, how do you decide between shipping features and fixing reliability? These questions don't have universal answers. The right amount of reliability for online banking is very different from the right amount for a social media recommendation feed. This is where site reliability engineering enters the picture, not as a job title, but as a framework for answering these questions with engineering rigor. And at the heart of this framework are 3 concepts that work together: SLI, SLO, and SLA. Let's start with crystal clear definitions. First one is SLI, Service Level Indicator. And SLI is measurement. That's it. It's a quantitative observation of how your service is behaving. For example, request latency, error rate, system throughput, or availability. Notice what these have in common. They are specific, measurable, and objective. Not the system feels slow, but P95 latency is 500 milliseconds. So, but you might be thinking, wait, what about CPU usage, memory pressure, or disk I/O? Those are metrics, but they are not SLIs. Here is why. SLIs must measure user experience, not infrastructure health. Your database server could be at 90% CPU utilization, so that sounds bad, right? But if all user requests are completing in 50 milliseconds with 0 errors, is there actually a problem? Conversely, your servers could be at 20% CPU, and that sounds healthy, right? But if a misconfigured load balancer is dropping 10% of requests, your users are experiencing failures. Infrastructure metrics are useful for debugging, but SLI measure what user experience. Next one is SLO, Service Level Objective. An SLO takes an SLI and adds a target. It's your internal goal, what you're aiming for. The key word here is internal. This is your team's goal. It guides your architectural decisions, your deployment strategies, and your prioritization. When someone says, should we deploy this risky feature on Friday afternoon, you look at your SLO. If you're well within your reliability target, maybe you take the risk. If you are barely meeting your SLO, you wait until Monday when the full team is available. And then we have SLA, Service Level Agreement. An SLA is a legal commitment to customers. It's a promise with consequences. Notice the difference. This has teeth. If you violate an SLA, you pay money or customers can leave without penalty. Here is the critical relationship. Your SLA must be looser than your SLO, which is measured by your SLIs. So the typical pattern is, for example, internal SLO is 99.95%. So then external SLA will be 99.5%. And here we have a gap for 0.45 percentage points. So that gap is your safety margin. It gives you time to detect problems, respond to incidents, and fix issues before you violate customer contracts. So, now that we have definitions, let's talk about the principles that makes this framework powerful. The first one is user experience is the only reliability metric that matters. This is the foundational insight from Google's SRE practice. So your infrastructure metrics are proxies, but not goals. Put simply, if users can tell the difference between 99.95% and 99.99% reliability, the extra 9 is waste. Let's say you run an e-commerce site. Your checkout service has 99.9 availability. That's 33 minutes of downtime per month. Your analytics dashboard has 99.5 availability. That's 3.6 hours of downtime per month. Should you invest more in the analytics dashboard? Absolutely not, even though it has worse reliability numbers. Because when checkout is down, customers can't buy. You lose revenue. When the analytics dashboard is down, maybe some product managers can see metrics for a few hours. So yeah, that's annoying but not catastrophic. Always ask, what does the user experience in this failure mode? Second one, reliability is a future with costs. Every increment of reliability requires exponentially more engineering effort. Going from 2 nines to 3 nines, that's your first level of effort. Maybe a few redundancy patterns, better monitoring. But going from 3 nines to 4 nines, now you need multi-region deployment, automatic failover, sophisticated circuit breakers. That's roughly 10x the engineering effort. And going from 4 nines to 5 nines, you'll need active multi-region, complex consensus protocols, chaos engineering, and this is another 10x multiplier. This 10x per 9 is a rule of thumb from industry experience, not a mathematical law. So your actual costs vary significantly based on current architecture, team maturity, and existing infrastructure. But the principle holds. each additional 9 is exponentially more expensive than the last. And here is the paradox. Perfect reliability means zero innovation. So every deployment is a risk. Every code change is a risk. If you want 100% reliability, the only way to achieve it is to never change anything. No new features, no bug fixes, no optimizations. The most reliable system is one that never changes and never improves. And this is where error budgets come in. And we'll get to that in a moment. Third principle is explicit is better than implicit. Unwritten expectations create conflict. Product manager thinks we need 4 nines reliability when enterprise product. Engineering lead thinks 99.5 is fine, where B2B tool used once a day. Neither wrote it down. Neither had the explicit conversation. And when an incident happens, it becomes political. Whose expectations were right? SLOs forces this conversation up front. You write down, we commit to 99.9 availability for the checkout flow. Everyone sees it. Product, engineering, leadership. Now, when an incident brings you to 99.85%, it's not a political debate. It's math. You violated your target. Learn why, improve, and move on. So, SLOs convert political debates into engineering discussions. Next principle, differentiative between internal goals and external promises. This separation is crucial and often missed. SLOs are aspirational. They are your internal standard. If you violate an SLO, the consequence is internal. You have a team discussion, maybe you pause future work to fix reliability, maybe you adjust your SLO if it was unrealistic. SLAs are contractual. If you violate an SLA, the consequence is external. You pay money, you lose customer trust, you might face legal actions. Imagine you set your SLO at 3 nines and your SLA at 3 nines. You're operating at exactly 3 nines this month. Then on day 28, a 2-hour incident happens. You drop to 99.7. You just violated your SLA. Now you owe customers money, you're writing apology emails, and your sales team is putting out fires. But what if your SLO was 99.95% and your SLA was 99.5? Same incident, you are now at 99.7. You violated your internal SLO. So you have a team discussion, maybe pause risky futures, but you are still well above your SLA. Customers don't even know there was an issue. This buffer is essential. Always set SLOs higher than SLAs. Let me pause for a moment. We're about halfway through part 1. You now understand what SLIs, SLOs, and SLAs are, the building blocks. Next, we'll see how they work together in 3 powerful patterns. Now let's talk about how these concepts compose into patterns you can apply. First pattern is error budget management. This is the most powerful concept in SRE, and it sells the reliability versus velocity tension. Here is how it works. If your SLO is 3 nines uptime, you are explicitly saying 0.9% downtime is acceptable. So let's do the math. 1 month equals 43,200 minutes, and 0.1% of these minutes equals 43.2 minutes. So that 43.2 minutes is your error budget. It's your allowance of unreliability. Now, here's where it gets interesting. How you spend that budget is up to you. Scenario A, conservative. You deploy carefully, test extensively, ship slowly. You use 5 minutes of your error budget. Congratulations, you were very reliable. But wait, you left 38 minutes on the table. You could have shipped faster, taken more risks, experimented more. You over-invested in reliability. And scenario B, aggressive. You deploy 10 times per day, ship experimental features, move fast. One deploy causes a 30-minute incident, another causes a 15 minutes incident. You've used 45 minutes. You're over budget. Now you have a problem. You exhausted your error budget and then some. Here is where organizational discipline comes in. You need an error budget policy that everyone agrees to in advance. This transforms the velocity versus reliability debate. It's no longer product saying ship faster and engineering saying slow down. Instead, we say we have 30 minutes of error budget left with 10 days in the month. That's a healthy buffer. Let's ship the future. Or we say we've used 40 of our 43 minutes with 15 days left in the month. We're over budget. Future freeze until we understand and fix the root causes. This creates shared incentives between dev and ops, product and engineering. Developers want to ship features. If they ship too fast and burn through the error budget, they have to stop shipping. So they're incentivized to ship reliable code. Ops want stability, but if they're too conservative and the error budget never gets used, product and leadership start asking, why are we so slow if we have reliability to spare? So they are incentivized to enable velocity. The second pattern is user journey-based SLI selection. Not all parts of your system matter equally. Your SLI should reflect critical user journeys. Let's take an e-commerce platform. What are the critical user journeys? For example, user browses product, user adds items to cart, user checks out, and user checks order. Do these need the same reliability? And the answer is no. For example, checkout is critical because money is involved. Browse products important, but degradation is tolerable. And order tracking nice to have, users can check back later. If your product browse service goes down, users can still check out items already in their cart. Annoying, but you don't lose transactions. If checkout goes down, you lose revenue by the second. Every minute of downtime is measurable in dollars. So different journeys warrant different SLOs based on business impact. Third pattern is compositional SLOs for distributed systems. This is where things get mathematically interesting and operationally complex. In a microservices architecture, a user journey spans multiple services. How do you calculate the reliability of the journey? Let's say checkout touch these services: API gateway, authentication service, inventory service, payment service, and order service. What the user experienced reliability. Here is where probability theory comes in. For a user request to succeed, all the services must succeed. So in probability terms, when independent events must all occur, you multiply their probabilities. If you're rusty in probability, think of it like needing to flip hats 5 times in a row. Each flip is 50%, but getting all 5, that's 0.5 multiple 0.5 multiple 0.5 multiple 0.5 multiple 0.5, and it equals 3.125%, much harder when combined. Same principle applies here. 5 services, each with 3 nines reliability, combine to give you 2.5 nines journey reliability. But what does this mean in practice? With 3 nines SLO, you have 43 minutes of downtime per month. But at 99.5%, you have 216 minutes. That's a 5x increase in downtime just from chaining dependencies. This is why microservices make reliability harder. Every dependency degrades your overall reliability. Important nuance: this serial dependency math assumes all services must succeed. But if you have parallel redundancy or fallback mechanisms, the math changes dramatically in your favor. For example, imagine you have 2 parallel payment processors instead of 1. So 6 nines from 2 3-9 services. This is the power of redundancy. So when architecting for high reliability, minimize serial dependencies and maximize parallel redundancy where possible. And we have some solutions. Set tier per service SLOs to achieve journey level 3 nines. Implement circuit breakers and fallbacks to break dependency chains. Design for graceful degradation. For example, show cached recommendations if recommendation service is down. And measure end-to-end journey SLOs, not just per service. In distributed systems, user journey SLOs matter more than individual service SLOs. And before we wrap up, let's look at how different organizations have interpreted these principles. There is no one right way. Google's SRE model, engineering first. This is where the term site reliability engineering originated. Google's model treats operations as a software engineering problem. SRE teams consist of software engineers who apply software engineering practices to operations problems. So they typically hired from a 50-50 split between software engineering and system engineering backgrounds. So 50% up cap. SREs spend maximum 50% time on toil. It means operational work, on-call, manual inventations. Remaining 50% must be engineering work, for example, automation, tooling, system improvements, and other stuff. If toil exceeds 50%, the SRE team gives the service back to the dev team. Error budgets are the primary framework for velocity versus reliability trade-offs, shared on call between SRE and developers. So operations is a software problem. Solve it with software. Next one is Netflix, freedom and responsibility. Netflix don't have an SRT team at all, because their philosophy is that every engineer is responsible for reliability. There is no separate team to hand off operational problems to. So how do they achieve reliability? Each service team defines their own SLOs based on a customer impact. Developers are fully on call for their services. Direct feedback loop between code quality and 3am pages. Chaos engineering as a reliability forcing function. Chaos Monkey randomly terminates production instances during business hours. If your service can't handle this, it's not production ready. Public dashboard showing real-time reliability of all services. Centralized platform teams provide deployment and observability tools. Company-wide incident reviews shared transparently. Learning from every failure. At Netflix, if your service goes down because a single instance failed, that's on you. Chaos Monkey proves your service wasn't resilient. This forces teams to build with redundancy from day one. Next one is Amazon, service ownership. Amazon's model is built on what their CTO, Warner Vogels, famously articulated in 2006. You build it, you run it, with strong platform support to make this sustainable. And development teams own operational reliability for their services. 2 PZ teams, small, autonomous, own service SLOs. Dedicated operation teams provide platform and tools, not operational support, service mesh, and observability standardized across organization. And here we have common misconceptions. More nines are always better. In reality, each additional 9 costs roughly 10x more engineering effort and slows deployment velocity significantly. 3 9% versus 4 9% is the difference between 43 minutes of downtime per month versus 4.3 minutes. For many applications, users cannot perceive this difference. For example, your internal analytics dashboard used by 20 product managers, accessed during business hours for non-critical decisions. And does it need 4 9%? No. Even 99% which equal 7 hours downtime per month, is probably fine. Your payment processing system handling millions of dollars per hour, absolutely yes. 4 9% or higher is justified. Second myth is SLOs are just monitoring thresholds with better names. In reality, SLOs are business-level commitments that drive architectural decisions, team priorities, and resource allocation. A monitoring threshold says alert when latency more than 500 milliseconds, and SLO says we commit to 3 9% of requests completing under 500 milliseconds, and if we violate this, we stop shipping features and fix their underlying problems. So, I've seen organizations create beautiful SLO documentation, put it in Confluence, and nothing changes. That's because SLOs without consequences are just wishful thinking. SLOs only work if they are measured continuously and accurately. There is an error budget policy everyone agrees to. Leadership supports the policy, and violating trigger action, not just discussion. So SLOs without error budget enforcement are theater. Third myth is SRE is just DevOps done right. In reality, SRE is a specific implementation of DevOps principles, using software engineering approaches to operations. DevOps is a philosophy. Break down silos, automate, share responsibility, continuous improvement. SRE is a practice. Specific patterns that implement DevOps philosophy. For example, error budget, 50% ops cap, blameless postmortems, toil reduction targets. You can do DevOps without SRE. Amazon's model is DevOps, but not strictly SRE. No SRE job title, but still exemplifies DevOps principles. But you cannot do SRE without DevOps. SRE requires the cultural foundation DevOps provides. So SRE is an implementation of DevOps, not a replacement. Next myth is you need microservices to do SRE. In reality, SRE principles apply to monolith, though implementation details differ. For example, monolith SLOs are often simpler. Single end-to-end SLO for the application, easier to measure, simpler, error budget. Microservices SLO are more complex, need journey-level SLOs spanning multiple services, require distributed tracing to debug violations, and compositional error budgets. But both can benefit from explicit reliability targets, error budget thinking, measurement, and data-driven decisions. So SRE principles are architecture agnostic. Implementation details vary. You now understand the core theory behind SRE. The framework. SLIs measure user-facing service behavior. SLOs set internal reliability targets. SLAs create external commitments. Error budget balance velocity and stability. The principles. User experience is the only metric that matters. Reliability has exponential costs. Explicit targets prevent conflict. Internal goals must buffer external promises. The patterns. Error budget management aligns incentives. User-journey-based SLIs measure what matters. Compositional SLOs account for distributed complexity. The approaches. Google, engineering first with 50% op cap. Netflix, developer ownership with chaos engineering. And Amazon, service ownership with platform support. SRE isn't about job titles. It's about engineering rigor for reliability. Now that you understand the theory, part 2 will show you exactly how to implement this. Minimum viable SRE. How to start with just a spreadsheet and one user journey. 4 real-world case studies. Learn from Etsy's error budget conflict, Slack's counterintuitive lesson, Spotify's microservices journey, and a fintech startup's instructive failure. Trade-offs and decision frameworks. How to set the right SLO for your context. Common mistakes. How to avoid the pitfalls that sync most SRE implementations, and action plan, your week-by-week implementation roadmap. The theory is powerful, but implementation is where teams succeed or fail. Join me in part 2 to turn this knowledge into practice.